First of all, let me ask you that how many OpenCL programmers have we here? Okay. So, hello and welcome everyone. My name is Balázs Keszthelyi. Sadly, I cannot tell you that many interesting things about my background as other presenters did. So, I've never been a kindergarten teacher in my previous life, and I'm educated to be a programmer. Actually, I'm just a regular, everyday, normal guy who likes local brewed beers very much, and sometimes watches the matches of Manchester United or the Hungarian national team. However, I don't recommend the latter one to anyone. There was only one weird thing about me, and I still feel ashamed of it, that I've never ever showed any sign of interest in sport cars. Instead, I've always been fascinated rather about fast GPUs. That's how, because being a GPU programmer is almost as macho thing as being a Formula One driver. So this is how I ended up being the lead programmer of CL Benchmark. Is there anyone here who heard of CL Benchmark? Oh yes, I almost feel like a pop star. After that, so I'm quite an old school guy also, so I build my own computer and I run Windows on it, and I don't go easily with IT trends like going mobile and things like that. But with the advent of GPU in mobile space, I became increasingly interested in mobile GPUs, and that's how I ended up joining Broadcom's efforts in order to develop GPUs. So Broadcom is generally an industry-leading company for connecting everything, but for the scope of this presentation, a mobile GPU vendor. So the original idea behind the presentation was that to show that how little we know about power efficiency programming. So developers have everything they need in order to optimize their software for performance. So there are white papers available, quite efficient, almost standard-like algorithms, and very interesting conferences about it. However, for energy efficiency, every transfer-C information is hardware-dependent, proprietary, and not published. For performance optimization, we have established performance metrics and tools, and even if we don't have any kind of profiler, it's not that hard to modify our code to use performance counters or timers. However, for energy efficiency, we don't have any good tools for localized measurements, so we can't tell which particular part of a device consumed how much power. Because of the available information and tools, most good companies has already implemented a process for profiling, finding the bottlenecks and eliminating them. However, for energy efficiency, in lack of information and tools, no such process could be implemented for companies. A very important difference between the two approaches, and it's quite game developing thing, that performance optimization focuses on bottlenecks, which is a good thing, but sometimes focuses on bottlenecks temporal too. So focus on the frames which has the highest frame rates. It's absolutely valid thing from user experience perspective, but besides it, at the end of the day, your battery won't be down because of those frames exclusively. It will be down because of your whole general performance. So for energy efficiency, you need to focus on the cumulative data. with that little knowledge about energy efficiency, developers may start to think that it's just another buzzword like the cloud or the next big thing, but luckily it's not. Because as a principle, we all know that energy is power by time, so if you can't do anything but optimizing for performance, and this way for time, you've already done a good thing. So actually, because you have to focus for cumulative metrics, it's a safe bet to consider energy efficient programming as a super optimization of your program, so to optimize everything, every part of it. The first thing you have to be aware of and you need to do carefully is to choose the right device which can execute your algorithm the most efficiently. Having the option of choose the device actually implies that you have more than one devices, which is the case. So for mobile space, you always have a CPU and a GPU. And the programming of it is already available for popular heterogeneous APIs like OpenCL and RenderScript on Android. So these two has very different goals, because RenderScript is generally a higher level approach focusing on the efficiency of development, but actually its main focus is performance portability, and performance in itself is just secondary, while for OpenCL everything, so the focus is about the performance. It's reflected in their availability, because you can program OpenCL only through the NDK, the CLK HRICD extension, while you can only program RenderScript from SDK, so practically Java code. It's a good thing in RenderScript that it has a full support from Google, so you're more than welcome to publish your application on the Play Store. However, for OpenCL you only have unofficial support, which actually means that it's not forbidden to vendors to support OpenCL, but if you upload your application using OpenCL, your application may be removed from Play Store. But don't worry too much about it, it's just politics. So, what is okay. So, what is I'm a bit ashamed of it, but I can't tell you any more details about energy efficiency, only the lack of details. The only thing I can do is to tell about the relationship of power efficiency and the common performance optimization techniques. So actually, I'm going to present these techniques in order of priority. This order is somewhat against common belief, so don't consider it as a strong statement in itself. Point 0 is about host to device and from device data transfers. So in mobile sector, everything is about power, and data transfer and the DRAM operations are definitely power-hungry beasts. So you have one good reason to reduce data transfers because of it. The other good reason is that without reducing the data transfer, it absolutely doesn't matter how much speed up you have achieved on the computation side, because by introducing additional server-client communication, you can easily lose that advantage. On the other hand, anyway, is the classical problem of accelerator devices, which is very different in mobile development than in desktop. That in desktop you have the GPU device has its own super fast memory with a PCI Express kind of barrier separated from the system memory. However, on mobile, these two things are at least physically the same. So logically not necessarily, because they may be accessed by different memory management units, but still you can keep the data where it is. So for OpenCL, it's very important to avoid the transfer semantics as much as you can. So prefer mappings everywhere. Prefer mappings and sharings, because that part of the API is just continue its advancement by introducing of shared virtual memory and other stuff in future versions. It's a good practice to not try to share your host memory allocations to the OpenCL, however it is possible, but rather to try to allocate every synchronized memory resource on the device itself, because this way you guarantee to have a proper auto-alignment. For render script, originally for allocations, you didn't have any kind of semantics for mapping and sharing, but luckily since 4.3 they have introduced synchronization with an underlying resource like a bitmap. Your other tool was that you can directly feed render script kernels with pointers, but they are host allocated memory, so it's not guaranteed that it has the proper alignment. From game developer perspective, if your computation is about modifying or producing new meshes or doing some post-process effects, it's definitely worthwhile to try to use OpenGL sharing where available. Actually, one more thing is that the reason why it's called 0.0, because personally I don't consider this stuff as an optimization step, so it's rather about the shame of a developer who doesn't even reach this level of optimization. So our first real point is about the memory access pattern. So historically, bandwidth was always a focus of OpenGL development, because with bandwidth limitation, your application instantly loses its scalability. GPU is not about doing the same things we've already done but more efficiently. It's about doing completely new kind of stuff, and for this new applications we needed more freedom, more control, and we got more responsibility and a way longer rope to hang ourselves with. So now we can do achieve data starvation many more than before, and yes, and render script was an exception originally, but luckily since 4.3 they've also introduced random access rights by settlemented. So the main thing is that you have to consider each of your data transfers not only on its own, but as a union of data transfers from neighboring work items. This union gives you the so-called memory access pattern. The most friendly and natural access pattern is the coalesced one, which is actually properly aligned and continues in a linear address space. Everything else you may face a decremented performance. Despite the trends on desktop development, on mobile it's especially a good idea to try to make use of images, because if your problem can be naturally expressed in a two-dimensional manner, so if you can profit from two-dimensional locality, images just guarantee it to you by some kind of magical two-dimensional caches and also magical internal representations. So this magic is actually dark magic, because there is no chance that any vendor would like to go into too much details about it, but you can assume that it's practically the same thing for different hardwares. Actually, I've advised you to do mapping as often as you can, but because of the different internal representation, mapping for images may have some cost. There's also one thing you should keep in mind, that if you want to use OpenGL sharing, then actually you can share images with textures and buffers with buffers, and there is no interaction between two distinct categories. And it can be important, so because if you are outputting a texture, then you should use images. However, even if you're outputting a pixel buffer object, it doesn't matter if you could profit from two-dimensional locality. Because it's a buffer, you should still keep using buffers. What is the ugly part of the story is the random access, which is the new stuff for GPU development. So for random access, the only thing you can do is to tune for probability. So you need to handle this thing on the data-oriented design level of your application. So you have to focus and evaluate that what kind of data are you reading and modifying together, and encapsulate those data and those data only. So generally you should prefer structure of arrays over array of structures. And this is because you want to reach as few cache lines as possible, and that's the way to do it. So it's a bit out of scope to go into details, but there are situations when it's still not good enough, and for those situations, which may seem completely hopeless, you may still consider to sort your data. And okay, so the sorting itself will introduce its cost, but you need to find the right balance between the cost of the sorting and the advantage you gain on the better access pattern. The second one is branching. So actually we already know a lot about branching. Some of you may already heard the word predication and stuff like that. So this is not the reason why they are the second. They are the reason because you are generally advised against branching, so you need to try to avoid it as much as possible, or use lightweight alternatives like the ternary conditional and the select operation for conditional assignments. So what is important to say that it's not entirely true. So branching has its effect, or can have its effect on the memory access pattern, and this way it can be particularly important as an optimization tool, because if you have random access to the memory, then if you can avoid it by introducing some additional branching, the cost of the branching is much less than the cost of the data transfer you want to avoid. So it generally can be a clear win if you can reduce the cache lines accesses this way. However, for Coalesced, it's on the contrary, because there is a great chance that you just introduce the cost of the branching, but the data you want to skip will be read or will be fetched anyway. So the rule of thumb is that every data transfer hurts, but the unnecessaries are the most. One common mistake I need to turn your attention to is that, however, the ternary operator and the select has very similar semantics, but actually the ternary operator has a lazy evaluation, while the select as a function is strictly evaluated. It's important because if you are writing a conditional to protect memory from out-of-range excesses, at least you got an error with using select, because a strict evaluation means that the arguments are evaluated first. So you read that memory you don't want to read before it's actually evaluated whether you want to read it or not. So for memory protection, at least you got an error. But if you do it for optimization purpose, no one will warn you about the fact that you still read this memory you didn't want to read. The third one is about the arithmetic operations. So I don't want to make these illusions. So in themselves, arithmetic operations are the dominant factor in power consumption, particularly the full precision floating point operations. Relaxed precision or half precision is way better, and theoretically integer operations could be just as fast and more power efficient than floating point operations, but the sad truth is that on mobile GPUs you can't really expect good support for integers, but maybe it's going to change in the future by more and more GPU applications out. So one thing you should focus there is to try to use built-in functions as extensively as you can, because built-in functions are not just the only way or so the best way for you to control precision and this way power consumption, but it's the clearest way to express yourself to the compiler. And don't have illusions. These compilers are working on limited resources, so you shouldn't expect too much optimization from mobile GPU compilers, and it's always true that there is no magic monkey in it, no matter how much banana you've got. So just write the code in a way it should be written. The other thing is that as floating point operations has the non-associativity feature that actually can cause the compiler not to do certain optimization, which may seem logical, but because it would affect precision, it simply can't do it. So however, I've advised you against to expect any compiler optimization. You should still allow it by supplying it as much information compile time as you can to allow certain common optimizations like constant evaluation or loop unrolling or stuff. The fourth one is synchronization. So, okay, if you have too many synchronization points, you're actually limiting the available parallelism of your application, but we all know that, we've learned that it's not very interesting. What is interesting, that synchronization is by definition is a kind of communication, and as a kind of communication it may introduce data transfers. So it's especially true for global atomic operations, because they are by nature harder to cache, and using global atomics extensively, you can practically flush out all your cache and cause DRAM operations extensively. The fifth one, and the last but the most complicated, is about the problem decomposition. It's complicated because you have simply too many things you need to balance, and it's also complicated because this is the first decision you need to make before the actual implementation. So generally, by having as much work items as you can, you just enable massive parallelability, which is a fine thing generally, because it's not just about execution width, but about latency hiding options as well. But as a negative side, if you have far more work items than optimal, then you're just introducing additional scheduling cost. Which is more interesting is to decide that how many work you want to do with a single work item. And under a single work item, I mean a single work item within a single kernel launch. So by doing as much as complicated stuff as you can, you may potentially reduce redundancy both in the computational and in the memory side, which is good. But doing more complicated stuff within a single kernel, so it has a higher probability that it's going to increase the register pressure. and after reaching a certain amount of register pressure, you just limit the available latency hiding options, and going even further with an extreme amount of register usage, you just cause register spilling, which is memory transfer, so a kind of our fiercest enemy. For OpenCL, you have another optional thing, is that you may emphasize on the workgroup level of the composition. This way, theoretically, you could make better use of local resources, this way reducing data transfers, which sounds good. And also you can determine by setting the shape of the workgroup. So I don't mean actually the size of it, but the shape of the memory access pattern too, which might be suboptimal anyway if the driver would decide it instead of you. But it's not guaranteed that you actually have on-chip local memory in OpenCL. Okay, you can query it, but if you don't have it, then you're just introducing additional redundancy from global to global transfers, and it's definitely not the thing you wanted to achieve. So in OpenCL, you have several queries about the device, so you may think that by query those things, you know everything about the device, but it's not true. So queries are a good thing, you should query everything, but you shouldn't try to adopt your algorithm based on those queries exclusively. So as I've already told, OpenCL is focusing on peak performance. It does not guarantee you performance portability, but it's not just a fact you need to accept, it means that you need to guarantee performance portability. For RenderScript, life is way more easier because you have absolutely no control over the composition. There is no concept of workgroups, and only the naive one is used because the allocation determines the decomposition itself. So at the end of presentation, I think you already know to be aware of arithmetic operations. I tried to turn your attention into the memory instead and its implications on mobile. Yes, so at the end of the presentation, I hope you've just got some additional motivation and inspiration to keep doing what you love to do and you do the best, to optimize everywhere, optimize everything, and endlessly until your performance goals are reached and beyond. So thank you. I think I've used too much of my time frame, so just have your questions personally. But what you need to know that if you are also interested in trying the other side of these things, so to developing mobile GPUs and stuff like that, so you could be welcome to Broadcom in case you're good enough. And the first test, actually the first test is that if you can spell my name correctly, you know my email address too, so this way you have the contact information. So thank you for your attention. Sorry, I've been just told that I may still have time to ask questions, so please go on.
Do we have sort of a rough idea the sort of proportional difference between memory access and ALU operations in terms of power consumption on various devices?
So the actual amount is hardware dependent, and this way I can't comment. And so the only thing you should So actually, it's not going to be an answer for this specific question, but it's way more likely that your limiting factor is the memory access anyway. So when your application is not arithmetic bound anyway, just focus on the memory access pattern. If it's already as optimal as it can be and coalesced, then after that you can focus on arithmetics. So, okay, is there another question? No, cool. Thank you.